everyone, Mr. Hannick here. Welcome to the new chapter on exponential and logarithmic functions. We're going to start off with index laws. So this is basically all revision from year 10, hopefully. In this video, for the first half, I'm going to outline all of the index laws and also give you examples of each one. And then in the second half of the video, I'm going to prove each index law to you. So if you want to, you only need to watch the first half and don't need to watch the proofs unless you're interested in them. So here we go with the first index law. And the thing with index laws to remember is they're not really laws, they're just sort of shortcuts, really. So the first index law says, basically if you have a to the power of n, and you multiply that by a to the power of m, that equals a to the power of n plus m. Okay, so just add the indices together. So let's do a quick example. If you have 2 to the power 2 multiplied by 2 to the power 3, that equals 2 to the power 5. And I might as well, there you go, there's an example. Okay, next one's very similar. It's basically the same law but using division. This one basically says if you've got a to the power n divided by a to the power m, you can just subtract the indices. That's a n minus m. So do an example of that. If you have 6 to the power of 10 divided by 6 to the power of 3, that is 6 to the power of 7 because we've subtracted the indices. Okay, so that's the first two. Moving on to the third index law. Third one basically says if you've got a to the power n, and then you do all of that to the power of m, then you can just multiply the indices. So that equals a n times m. So an example of number 3. Suppose you've got, let's say 5 squared, and 5 squared to the power of, let's say 6, then all you need to do is 5 to the power of 12. We've multiplied the indices. Super easy. Now, index law number 4 basically says a, if anything at all to the power of 0 equals 1. So here I'll do two examples. Example is 9 to the power of 0 equals 1. Another example might be 6x squared times y to the power 3 multiplied by 6 to the power of 2 or to the power of 4, and then do everything to the power of 0. Just forget everything because it's all to the power of 0. It equals 1. And I might as well do one final example. 2 multiplied by 6x to the power of 0. Well, that's, the 2's not to the power 0, so it's 2 times 1, because this is 1, and that equals 2. Okay, so that one's a bit more of a thorough example that time for question 4. Now, index law 5. Okay, so this is when we're dealing with stuff in brackets. So if we've got a times b all to the power of n, that's just a to the power of n multiplied by b to the power of n. So the index comes down to both of them. So let's do an example. An example might be 2x plus 1 and everything squared. What that equals is the 2 squared, multiplied by x plus 1 squared. This index has come down here and also here because everything in the brackets was squared. So then you can simplify that. 2 squared is of course 4, x plus 1 squared. So there's an example of that law in action. Law 6 is very, very similar. It's if you've got a divided by b and everything is to the power n, then that's just a to the power n divided by b to the power n. So I'll do a quick example. I'll do a much easier example than this one perhaps. I'll just do 2 over 3 squared is 2 squared over 3 squared, which equals 4 over 9. So there we go, there's number 6. Alright, index law number 7. Okay, this one has to do with negative powers. So if you have a with a negative indice, a to the power negative n, that equals 1 divided by a to the power of n. So we've been using this one before, but let's do a couple of examples anyway. If we have x to the power negative 2, that's the same as 1 over x to the power of 2. Or if you have x minus 3 to the power of negative 2, that is 1 divided by x minus 3 squared. Or an easy one is 5 to the power negative 1 is 1 over 5. So there we go, that's number 7. And number 8, the last one, is fractional indices. If you've got a to 1 over n, well, that just equals the nth root of a. So let's do an example. 8 to the power of a third equals the cube root of 8, which equals 2. So there's one example. The reason that's the case is because 2 cubed equals 8, and cube root is basically the opposite. So there's that. There's that one for us. Some people like to include a 9th one. I kind of think it's not really one, but I'll throw it in anyway, which is if you have a and you've got m divided by n, that is, it's still the nth root because you've got that 1 over n, but it's 8 with an m there. So I'll do an example to explain what I'm talking about. If you say you've got 8 to the power of 2 over 3, well, that is 8 squared with the cube root bit there. So you've got two ways of doing this. You can do the 8 squared first, or you can do the cube root bit first. It doesn't really matter. I'll do the 8 squared bit first. So that gives the cube root of 64, and that equals 4. The reason is because 4 cubes, which is 4 times 4 times 4, equals 64. So, so there you go. The reason I don't personally bother including this one is because it's really just a combination of number 8 and number 3. It's really just using 3 and 8 at the same time gives this number 9 here. So I don't really bother with it. Alright, now I'm going to do one big example that uses lots of these index laws, and then after that I'm going to prove them to you. So first, a big example that uses lots and lots of them. Okay, so here's my big beast of a question that I'm going to be simplifying. So, the first thing I'm going to do is this bit here, because I know the squared is going to come down and multiply through by this 3, this minus 2, and this silent sort of 1 that's there. But I'm also going to deal with this side at the same time because I can, and it's going to save me some sort of working out space. So here I've got an x cubed, x to the power 3, divided by x. So I can do the 3, take away the 1 that's sort of there. So it'll give x squared. And I've got y to the power 1 divided by y to the power 1. So that will give me y1 minus 1 is y0. Then I've got z to the power of minus 2 divided by z to the power minus 1. So that's going to be the minus 2 take away minus 1. In other words, minus 2 plus 1. So that's going to give me z minus 1. Maybe I should I'll put a dash line here just so I don't get confused about what's the question and what's not. Okay, now I've got times this 2. I'm actually just going to put that 2 out the front here because it really doesn't matter which order I do my multiplications in. So times, now I'm going to do this bit here. So I'll bring the 2 inside the brackets. So that's x 3 multiplied by the 2 is 6, x to the power 6. Then y minus 2 times 2 is minus 4, y minus 4. And this is a z to the power 1, so 1 times 2 is 2, so that's z squared. Okay, so now I have a lot of things. Firstly, I notice that I've got a y to the power of 0. Anything to the power of 0 is 1, so I can cancel that one out and forget about it. Now I've got a lot of things multiplying through, so everything here is multiplying through, so that's going to be a lot of adding of indices. So I've only got one actual number, so I'll keep that number 2. Now x squared times x to the power 6, I'll add the indices, giving me x to the power of 8. Now the y's, well that one's cancelled, I've still got a y to the minus 4. And z to the minus 1 times z to the power of 2. I'll add minus 1 and 2 just to get z to the power of 1. And there we go, I've finished. That is fully correct. Sometimes questions will ask you to give everything in positive indices, in which case I would have to make y to the negative 4. I'd have to change that into y to the power 4 underneath the fraction as the denominator. So there we go. I've fully finished that one there. Now, just for fun, let's suppose that everything all along, put big brackets around everything, if it all had a to the power of a half. So let's imagine if we got to this stage and everything had a big to the power of a half. What we could do is then we'd be doing 2 to the power of a half, 2 to the power of a half. Now the 8 gets multiplied by a half, so that's x to the power 4. It'd be z to the power of a half. And y, 4 times a half is 2. Now a half is the same thing as square root, so that'd be the square root of 2 times x to the power 4, multiplied by the square root of z, divided by y squared. And then we've got 2 square roots, so if we wanted to, we could sort of combine those. So it'd be the square root of 2z, and then there'd be the x to the power 4 over y squared. So we could represent that in this form, if we wanted to. So there we go. There's a big nasty example of using index laws. What I'm going to do for the rest of the video is to prove to you all of the index laws. And I'm going to prove that they're basically just shortcuts. So if you want, you can stop watching this video now. But if you're interested in the proofs, then stick with me and we'll go through them. So let's have all our index laws back. And I might clear up some room and do the proofs where I've previously done these examples. Okay, so here we go with the first index law. I'm going to start off not by proving it, but by verifying it, which is different. Verifying basically means showing that it works. So to verify basically means showing it works, showing that it works. Showing that it works for one or more examples. So verifying is different to a proof or proving something. A proof is basically showing that it will always work. Showing that it will always work. And the key bit here is always, showing that it will always work. So I'll show you what the difference between verifying and proving is with this first index law. So first I'm going to do a verification. So verification is sort of like an example really, but spelt out a bit more. So let's suppose we have 2 to the power 3 multiplied by 2 to the power 4. Okay, well let's write 2 to the power 3 in expanded form first. That's 2 times 2 times 2. And now it's multiplied by 2 to the power 4. So I'm going to write 2 to the power 4 in expanded form as well. 1, 2, 3, 4 more 2's. Now I'm going to take this thing and write it back into index form. I've got 2 is my base number. And I've got 1, 2, 3, 4, 5, 6, 7 of them. 2 to the power 7. And you notice that 2 to the power 7 equals this 3 plus 4. So there we go, it's verified. I have shown that it works for this one example. Now, a proof showing is something that shows that it will always work. So a proof will look more like this. A to the power n by a to the power m equals a times times a. And we can say there are n a's. Now multiplying by a times a times a times times a, and here we can say that there are m a's, and so now we can say that equals a to the power n plus m, and that is our proof. We are done. So one of them is sort of the proving one. This is the proof here, proof. So one of them uses only algebra, I guess, to show that it works every time, and the other one uses actual numbers. So often people find verifications a bit easier to follow. So some of these will be using verifications and some will be using proofs. Okay, let me clean up my space again, and we'll go for number 2. Okay, so for law number 2, I'm just going to do a verification, I think. So let's say 5 to the power of 6 divided by 5 to the power of 4. Well, that's going to be 5 times 5 times 5 times 5 times 5 times 5. So there's 6 of them, divided by 4 of them, 5 times 5 times 5 times 5. Now every time there's a 5 divided by 5 is 1, so you can cross them out, and we can cross that pair out, and those ones, and those ones. So now we've crossed everything out, and we're left only with 5 times 5, which of course equals 5 squared. And you notice that 6 minus 4 is 2. So there we go. That's a bit of a quick run through from number 2. So that is number 2. Alright, let's have a look at number 3. So we're looking at number 3 next. I'm just going to do a verification for this one too. So let's say that we've got 2 to the power of 2 all to the power of 3. Well, that is because there's 3 lots of 2 squareds. So there is 1, 2 squared, 2, 2 squareds, 3, 2 squared. So it's 3 lots of 2 squared. Now each one is 2 times 2, 2 times 2, 2 times 2, and they're all multiplied together. Now we can write it in index form again, 1, 2, 3, 4, 5, 6 2's. So it's 2 to the 6, which is obviously the same as 2 times 3. So there we have it. Number 3 is done. Okay, number 4 is a bit more interesting. We're going to start with our number 2 result. Okay, so our law for number 2 is AN over AM. And let's say here that N and M are the same thing. Okay, so from this, and we know that it's going to be the top one minus the bottom one. So from this, we might have AN divided by AN. It's going to be AN minus AN, sorry, AN minus N, which is A0. Okay, so we're going to see what happens when we have AN divided by AN. Well, AN divided by AN is the something divided by itself. Whenever you have something divided by itself, that equals 1. Because anything divided by itself is 1. For example, 2 divided by 2 is 1. X divided by X is 1. And so therefore AN over AN must equal 1 as well. So there you go. Anything to the power of 0 must equal 1 because of that. Okay, so we're up to index law number 5. Okay, number 5 here. So it's the one that says, oh, you can just read it there. So let's suppose we have, I don't know, 2 times 3 all to the power of 3. So that means we've got 2 times 3 That's one of them. Multiplied by 2 by 3, that's another one. By 2 by 3, that's another one. Now we can sort of rearrange this to make it look a bit more ordered. So because multiplication can happen in any order, we can gather all the 2's together. So there's that one, and that one, and that one. And similarly, we can gather the 3's together. And this gives us 2 to the power 3 multiplied by 3 to the power 3, which is this 3 coming down here and this 3 coming down here. So it's all, that one has been verified. Now, number 6 is a over b to the power n equals a n over b n. Now this one we could do in an extremely similar way to this one, but in a way it's more fun to just use the index law number 5 to prove number 6 and say that what if the b from this one actually equals, so let's say we have a and x to the power of n equals a to the power n x to the power n, which is what we've sort of already proved, if you like. But then what if we say that x equals 1 over b? So then suddenly we have from here, we've got a over b to the power n equals a to the power n and 1 over b to the power of n. And so from this we can sort of see that this is going to be true, because you can do the, this is a n multiplied by 1 over b, oops, times 1 over b times 1 over b, you know, n, whoops, n times. So from that we have a n over b n, and you're done. So there we go, that's number 6 taken care of also. Okay, so next we're going to be having a look at index law number 7. Okay, to do this one we're going to whip out our index law number 2. A to the power n equals a to the power m, which is a n minus m. Now what we're going to do is say that n is equal to 0. So we'll have a to the power 0 over a m equals a 0 minus m. Now a to the power 0 is of course equal to 1. We did that in index law number 4 here. So we've got 1 over a to the power m equals 0 minus m is a to the minus m. And this of course is nothing other than index law number 7, so we have proved it, we're done. Okay, so now we're up to number 8, which is in some ways the trickiest one to prove. So first we know that if we do the square root of a times the square root of a, we get a, which is the same as a to the power 1. We also notice that a to the power of a half times a to the power of a half is also equal to a to the power 1. So here you could just make the inference that therefore square root of a must equal, these two things must be equal here, because these are the same and these are the same, and that's kind of alright. But there is in fact a better way to do it, which is then to think, well, here a square root of a times square root of a is the square root of a squared, and the square root of a squared equals a to the power 1. So if we want to get this, this bit here to 1, what we need to do is one of these times things from rule number 3. So if we take this whole thing, the square root of a squared, and then do that to the power of a half, well that must equal this 2 will be, the 2 will be multiplied by the half, 2 will be multiplied by the half, which just gives the square root of a, because 2 times a half is 1. And we need to do the same thing to both sides. So if we do the to the power of a half to this other side as well, then we get a to the power of a half. So here we have the square root of a equals a to the power of a half. And this will work equally well if you think the cube root of a times the cube root of a times the cube root of a equals a to the power of 1, then that's the cube root of a to the power 3 equals a to the power 1. Now we'll do both sides to the power of a third. So if we do both sides to the power of a third, both sides to the power of a third, then that gives us the cube root of a is equal to a to the power of a third. And you can just sort of keep going or make an inference that that will continue on forever. Okay, rule number 9, this very last one here, rule number 9 that says a m over n equals n root a m. It's just a combination of rule number 3 and, hang on a sec, maybe I meant rule number 5 and rule number 8, the one we've just done. So you can just write this as a to the power m, all to the power of 1 over n. That's by rule number 3. Then this 1 over n business, through rule number 8, we can write the 1 over n as the nth root of a to the m of this stuff. And we're done. So that rule was extremely easy to prove. That one all proven. So there we go. All of those index laws are proven. So well done for sticking with it right at the end, and feel free to ask me to actually prove for you any of the ones that I only verified if that's what you're after. Alright, see you in class.